Hello everyone and welcome to lecture 3. Today we will be talking about derivatives. We will show you how you can use Mathematica to do different kind of differentiations. And without further ado, let's get started. So first I want to declare a function, let's say f of x. And I want to take a very simple function. Let's say I want to take sine of x. So we have declared our function, we run the code. So how we can differentiate it? Well, there are two ways. The first one is that we can simply type f, give it a prime, and let's try to run this code. As you can see, it is giving us some result, but somewhat a bit ambiguous. So let's do this, f prime of x, right? And as you can see, we can get the derivative as cosine x. But what if I want to do differentiation again? That is, I want to evaluate the second derivative of this function. Again, you can type f and you can type prime 2 times x, run this code, you get a minus sign, and you can continue to do so. But what if I want to get the nth derivative of this function? So in those cases, using this prime notation in Mathematica is not that helpful. So there's another command to evaluate derivatives, and that command will work for not only single variable functions but also multivariable functions, and that command is d. You just type capital D, put a third bracket, and if you put your cursor over here, you can see that this will give the partial derivative del f by del x. So f is a function and x is the variable. Now note that it doesn't show you the full functionality. To know the full functionality, you have to click on this information icon, but I won't do that right now. We'll be showing you how to get derivatives of multivariable function in the upcoming lectures. So let's say I want to take the nth derivative of this function, that is the sine function. So I'll just go on around here, I'll type f of x. Now instead of just x, first I have to put a comma. Instead of just x, since I want to take the nth derivative, first I'll put x, I'll put a comma and n. Let's see what happens. As you can see, this is my nth derivative. Now what if I wanted to do the second derivative? So instead of n, just type 2, shift enter, and as you can see, these results coincide. So this is how we can use the d operator to determine the derivatives. But let's say I want to evaluate the derivative of sine function at a particular point. Let's say x equals to 0.5. How do I do that? So the way to do that is to do the following. Again, I'll just type for you. Notice that whenever you are typing this expression, that is, you are just giving only x, it will automatically understand that you are trying to evaluate the first derivative. Alright, and to evaluate the value of the derivative at x equals to 0.5, what you need to do, you need to put a slash, then you put a dot, then you type x goes to 0.5, and as you can see, we have our desired value. And if you don't believe me, you can just take x equals to 0. So that should give us 1, right? It is giving us 1. Yeah, exactly. Now this will work even if you have multiple functions. Let's say I want to define another function called g of x as, cosine of x, and I want to do f of x times g of x. I want to see that whether this operator will work for this expression where these two functions are multiplied, that is the function of sine multiplies by the cosine thing. And I want to see the second derivative, x comma 2. You can see the answer comes in a heartbeat. Note that instead of declaring functions, I could write sine and cosines over here. That is, instead of f of x, just type sine, and instead of g of x, just type cosine, and you run it, the result is the same. You can also take third derivative and stuff like that. And also you can see that I'm getting some suggestion bars. If you just click on this suggestion bars, you can get the desired results. For example, since you guys are familiar with plot and simplify, let's go for simplify first. If you just click on it, it will simplify this expression for you, and if you click on plot, it will automatically plot this expression for you. Okay, so we saw how to deal with derivatives in Mathematica, and you can use this d function, that is the command d, to get derivatives of your desired function. Okay, now let's take a look at some logarithmic differentiation that you guys are familiar with from Math 110 or basic calculus courses, that is courses from differential calculus. And we want to evaluate expressions like the following. Let's say I want to have this expression, x to the power sine x. I want to differentiate this kind of expressions, that is to find the derivative of this kind of expressions. So how do I do that? Again, the answer is very simple. In Mathematica, just type d and you just input your expression. Sorry, S should be capital, and then you specify the variable, and there you go. Again, you can also simplify the whole result just by doing this, put double slash and simplify. But it's better to do it like this. Instead of using simplify here, it's better to use simplify in front and then put this whole thing into the argument of simplify. And as you can see, this is your expression. Now let's talk about implicit differentiation. So let me just put up another section, implicit differentiation. I hope I got the spelling correct of differentiation. Yeah. So here we want to evaluate expressions like the following. Let's say you have an equation that tells you that x cube minus 5xy squared plus y cube plus 11 equals to 0. So then you ask the question that what is dy dx. So this is pretty easy if you are familiar with implicit differentiation, but today we will look at how to do this in Mathematica. So let us first type this expression. Note that we are not declaring a function here right now. So what we need to do is to first bring up our d operator, and we have to type this expression inside this d operator. And while doing that, we have to keep in mind that this y is a function of x. So that's why we will write y, then we'll put a third bracket, and then we'll put that x inside the third bracket. Let me type it for you and things will be clear. So first type x cubed, then minus 5x y squared plus y cubed. But there is a catch. See, I have only typed y here. So if I don't specify that y is a function of x, Mathematica will just treat it as a constant. That is a symbol that he doesn't know. So instead of typing like this, let's type it like this. You put your first braces over here first, then type y is actually a function of x, then you put the square. I could have written this square without typing these first braces, but just to be on the safe side, I have given this first braces. So instead of y cubed, just type y, oh sorry, y cubed. Okay, and then we have plus 11, and then we want to type double equals to 0, so that Mathematica knows that it is a equality, that is the left hand side is equal to the right hand side. That's why we have to put double equal sign. And then what we want to do, we want to give a comma, and since our variable is x, just type x, and let's see what this gives. As you can see, this is giving us an expression that involves this y primes, right? And if we solve for y prime, that is dy dx, we will get our desired result. So how to do that? Note that before I go on, note that this will give you a suggestion called solve ODE, and this means solving this ordinary differential equation. Do not go for that, because we are not solving this differential equation, we just want to evaluate y prime. That's why I'm not clicking on it. So to do that, we introduce another command that comes with Mathematica, and that is called solve. If you just type sol, solve, put third braces if you want to know functionality again. So just put this cursor over here, and what this solve command does, it takes the expression and it tries to solve this expression, that is the system of expressions. You can also have systems of it, but for us it's just one expression, and you have to specify the variable, that is the thing you are trying to know. So what I want to do, I just want to copy it so that I don't have to type anymore. So copy and paste it, but here again you have to put this equality, because this is our expression. From this expression we can get y prime, right? And what is our variable here? The variable is the thing we want to know out of this expression. That's why the variable will be y prime of x. Just hit shift enter, and there you see, that's the y prime, or the dy dx, that is the derivative we are looking for. And let's say you want to plot this thing, that is, you want to plot it. So how do we go about that? How can we plot this function? It's a two variable function, right? It seems like it, but here y is a function of x. It's not a two variable function. It seems like 1, but it's not, because it's bounded by this equality. It could have been a function of two variables if I have written, instead of 0, I had written f of x, y. Now you might say that I can always have a function whose value is 0, and that is okay as well, but let's not complicate our lives at this point. So let's focus on treating y of x, that is y is a function of x, and we want to plot it. So in the last lecture you guys saw how to plot functions of a single variable, and here you cannot use that plot. So what we will do, we will use the contour plot, a new command. So yeah, let me just use contours. So type con, and as you can see, you will see an option called contour, TOUR, plot. So what does contour plot do? It takes a function, it generates a contour plot of f as a function of x and y. Alright, so let's follow this instruction and see what happens. And again, let's just take our expression over here. By expression I mean this one, just this guy, not equals to 0. We are not taking this part. X cube, I'll just go with the power symbol right now. 5xy squared plus y cubed plus plus 11. And then first you need to specify the x values, that is the interval of x. Let's say -4 to 4, and for y let's say -6 to 6. You can take any interval you want. Now let's try to do it. I see what happened, because I haven't put a, yeah, you see a few seconds back that it didn't generate any plot when the x and y were together like this, that is there was no spacing or multiplication symbol between them. So what happened is that Mathematica took this xy squared that are stuck together to be a single symbol, and for this symbol Mathematica didn't know any value, so it couldn't plot it. Let's do it again and we'll see that there is no plot, there is no picture. And if you just separate them by a space or a multiplication symbol, there you have it, that's your contour plot. Now we will take a look at another example of an implicit differentiation. And now what we want to do, we want to let's say I have this expression. The expression is y sine 2x equals to x cos 2y. I should put a space over there, and we want to know what is dy dx equals to what. Again, this is a matter of implicit differentiation. So what we will do, we will just type this d, type y, then we specify y is a function of x, we type sine 2, put a space or a multiplication symbol. Let's do it with the space now so that you get comfortable with it. Put double equals x cos 2 space y, but here also you have to specify that y is a function of x, and then you just, oh sorry about that, specify the variable x, and again you have an expression that involves y prime. So how to do that? Type solve. Now what I'm gonna do is a little bit different from what I did earlier. I'll just use a percentage symbol and see what happens. I'll just type y prime of x. As you can see, it's giving me the correct answer. So the percentage symbol actually took the expression that came in the last line, that is on line 28. So it just put it over here, and then we use this solve to get our y prime, that is dy dx, the derivative. And let's try to plot this y sine 2x equals to x cos 2y. Again we will use contour plot. Oh sorry, it was in another format. Contour plot. I'm going to type y space sine 2x, then equals x cos 2y. Yeah, that's right. Okay, and let's say x runs from -6 to 5, and y runs from let's take -3 would be too small, so -7 to 9. Let's see. So this is an interesting plot. So what you can do is that you can open up any calculus book and take some functions from there that require implicit differentiation. You can plot them like this, and you'll see some many interesting plots. So this will be it for implicit differentiations, and the next thing we want to see is called series expansion. So let me type that up. Series expansions. So first let's talk about what is a series expansion. So from your calculus course you are familiar with the Taylor and the Maclaurin series, so we'll just use that. That is the power series expansion, right? Those are in fact power series expansions. So how to do series expansion in Mathematica, that's the thing we want to see. So let's take our favorite sine function and we want to expand it around x equals to 0 and see if we get the result that we are familiar with from our calculus courses. So to do that, just type SE and you will see that a suggestion is coming up called series. To know what it does, again just put your cursor over here. It tells you that put a function f, that is the function, and if you use the series command, it will generate a power series expansion for f, that is our function, about the point x equals to x0, and this n is the order. That means this order means the highest power of x. Let's see how does this work. This example will make things clear for you. I want to evaluate the power series for sine x, and then I type the variable x, then I specify a point, let's say 0, that is I want to expand around point 0, and I want to do it up to power 4. I run this code, and as you can see, the series expansion for sine contains only the odd powers. So the first one is 1, second one is 3, the third one is 5, and as you can see, since I have truncated my series around when the power of x is 4, you can see that there is a O x to the power 5. This means order of 5 and higher. So these terms are not there. So what if I try 10? That means I want to see the terms that contains a maximum power of 10 over x, and I don't want to see things like x to the power 11, x to the power 12 and all that. If you run that, you can see that this 5, 7, 9 they're there, and from after 9, that is the X to the power 10, it doesn't exist in sine series because the coefficient is 0, it's not there. So from 11, 13, all this higher order terms are truncated. And this is just 1 factorial, this is 3 factorial, this is 5 factorial, this is 7 factorial, and all that. Mathematica has put at these values for you. And this series command is useful in many ways, because sometimes we are interested, let's say you are dealing with a problem and you get a final answer in terms of some special functions, and maybe we will see some special function in the later lectures, but not today. Sometimes you will see that while solving a problem you might come across with a special function, and to get some interesting solutions you have to look at the asymptotic expansions or the series expansion of that function. So in those cases this series command will be very helpful. So let's take another example just to see how series thing works, this whole series stuff works. Let's say I want to do series, I want to write a complicated function, let's say x cube, then I want to go into the, no sorry, not here, I want to say x minus 1 squared, and I want to type a plus sine x. Now I want to expand this function around x equals to, let's say 1, and notice that this x equals to 1 is in fact is singularity of this function, because when x approaches 1 this whole thing blows up, right? Because when x approaches 1 the denominator goes to 0, the whole thing blows up. Let's see what Mathematica tells me about expanding this function around this point. I want to take order of 5, and yes, it does give me something, so that is pretty cool. And again you can see that Mathematica will suggest you to do some stuff, truncate higher order terms, coefficient list, nth coefficient. If you type if you click on coefficient list, it will just give you these coefficients in a manner where they're listed, that is, it's a list thing. And as you can see that Mathematica is showing us that coefficient list, this thing is not a polynomial. So in certain situations Mathematica will often give you comments or warnings, whatever you want to interpret them as. Mathematica will set some conditions for itself, and it will try to evaluate the expression that you give it, and if it comes across any problem it will just give you a warning, or it will show you a comment that you'll understand. So this will be it for today, and I hope you enjoyed it, and I will see you guys on the next lecture. Thank you.